Hello and welcome back to the course Student Guide to Information Theory and Coding. In this session, we will focus on the Lempel-Ziv-Welch coding. In the previous session, we have understood the basic version of the Lempel-Ziv code, that is LZ77. So before going for Lempel-Ziv-Welch, we will understand this at the second version of the Lempel-Ziv code, that is LZ7H, its encoding and decoding example, and then we'll focus on Lempel-Ziv-Welch code, how we can do the encoding and decoding through some examples. And in the end of the session, we will take one practical application of Lempel-Ziv-Welch applied to the image transmission process. So, as we have covered in last lecture, the Lempel-Ziv algorithm, which was just focusing on parsing the binary data and creating a Lempel-Ziv code for the data compression. This basic Lempel-Ziv code, its advanced version is been developed with the name LZ78, where little different approach is used as compared to the basic Lempel-Ziv code. Here the approach is used to build and maintain the dictionary, where the algorithm works LZ77, that is the basic version, it is called as LZ77. Here the algorithm works on past data, whereas LZ78 algorithm attempts to work on future data. So this is the basic difference between basic LZ version called as LZ77 and the version LZ78. Here our focus will be on the future data while designing the subsequences in the data. This is done by forward scanning the input buffer and matching it against a dictionary it maintains. It will scan into the buffer until it cannot find a match in the dictionary. At this point, it will output the location of the word in the dictionary if one is available, the match length, and the character that causes a match fail. The resulting word is then added to the dictionary, right? So a little difference is there between LZ77 and LZ78. LZ77 works on the past data, LZ78 works on the future data. Let us try to understand this particular implementation of LZ78 by going through certain example of encoding. Now in LZ77, we understood the encoding of the binary data. Here, we will try to focus on the encoding of the letter data or the real-time data in the term of alphabets. Let us try to apply LZ78 compression algorithm on the string data, that the string data consists of certain letters arranged in the certain sequence. The letters are ABB, CB, CA, BAB, CAA, BCAAB. Now this is just a sample string sequence that we have considered in order to understand the algorithm LZ78. But in real life, we understand that we do not get such kind of continuous letter. We generally form the sentences by using the words, and the words, they can be created by using different letters in the alphabet system, right? So this is just a sample example to understand how the algorithm works. The similar way you can apply this algorithm to the real life data if you understood the steps given in this particular example. As I mentioned, LZ78 works on future data. So that's why we have to go on scanning this particular data sequentially from left to right, and we also have to create here the comma separated phrases, very similar to the case of LZ77. So here the comma separated phrases we can generate by looking at to the bit stream in the exactly same manner how we have considered it for LZ77 or basic LZ algorithm. So I will look at to the data stream, and in the data stream, if I just focus here on the first letter, that is A. The letter is A. A is a unique or innovative bit. Therefore, A I'm going to add as a comma separated phrase in my string table. So my first A is nothing but the comma separated phrase A. Then B is also an innovative bit. So B can be also considered as a comma separated new subsequence as B in the string. Then I'll focus on third character, that is B. B is already present here. So I have to take one innovative bit C over here. So BC is a new innovative string that I'm going to get over here. So that is considered as the third substring in my sequence BC. So BC is been recorded as third substring in my sequence. Next, B is already present, C is already present, BC is the previous string that we have, one innovative bit that we will add here forming the fourth string BCA. So BCA is going to be my fourth string. Then I'll focus on B, which is already present. BA is not present. So BA is a new substring that I'm having with one innovative bit as A. So BA is going to be my fifth string over here. Then once again, for rest of the data, B is already present, BC is already present, BCA is also already present. What I have to take is BCAA. A is my innovative bit, and I'm going to get sixth string for this particular sequence. So that we have recorded in the table as the sixth string in the dictionary BCAA. Then for seventh, once again, I have B with me, I have BC with me, BCA with me, BCAA is also with me. B is going to be my innovative bit. So BCAAB is going to be my new sequence substring in the dictionary as the seventh substring, which I have recorded here as the seventh substring. Now, I have created the comma separated substrings and these are been recorded in the dictionary. Next column, I have given index to this particular strings, the index which I have already mentioned in the top, like this is my first index string, second index string, third index string, like that, 7 index strings I got, and there they are recorded in the dictionary. Now I want to generate the output code by using LZ78 algorithm. So how I'm going to create this output code? The output code is very simple. I have to take the last character of the string, which is my innovative bit, last character of the string, which is going to be my innovative bit over here, and at the first part I have to take the index of that particular character. Now we understood from LZ77 scenario, A is a single string subsequence which does not have any prefix, right? So we have to focus on the prefix condition of this particular sequence. So I observe that A is my innovative bit and there is no prefix present prior to A, right? So as the prefix is not present prior to A, we can consider it to be 0 as the output bit. So whenever there is no prefix present before A, by default output is going to be 0. Very similar to LZ77 where we take null as the output. Null is the 000 sequence in the previous example. Here null is simple 0 digit prior to A. Similar for B. B is my second substring and I observe that there is no any prefix for this particular B. So no prefix, that means my initial output bit should be taken as 0. Now I will come down to the third string. C is my innovative bit. So C has been copied down here in the output as the innovative bit. What is my prefix? Prefix is my B, and this B is present at index number 2. B is present at index number 2. Therefore, whatever this C that I want to transmit, I will transmit the index of B as 2, C. I hope the things are cleared. Once again, I will repeat. I have to copy down the innovative bit at this particular location. C is my innovative bit. So C innovative bit has been copied down here. Then prefix is B, and B is a string whose index is 2. That index 2 is been taken in the output as 2 comma C. Similarly, if I look at to this particular case, A is my innovative bit. This A is been copied down here as it is. Then BC is going to be my prefix. So this prefix is a string present at this particular location, and the index of this BC is 3. Therefore, my output code is going to be 3 comma A. Same thing I can go on applying. If I look at to the last case, B is my innovative bit. B is been copied down here as it is. Then BCAA is my prefix, and BCAA is present in the this particular string whose index is 6, and this 6 index is been copied down here as the output code 6 comma B. I hope you have understood. The concept is very similar to LZ77. The only thing is what? The only thing is you could able to apply the thing on the strings, and whenever you apply on the string, the output will be an innovative string along with the index of the previous substring. So what is my output? Output will be 0 comma A, 0 comma B, 2 comma C, 3 comma A, 2 comma A, 4 comma A, and 6 comma B. This is the my complex message which I can transmit from transmitter to receiver. I hope the things are clear.
Yes, sir.
Okay, let us focus on now how we can do the process of decompression at the receiver end if I'm going to receive a certain code word for this particular LZ78 algorithm. So LZ78 decoding part that we are going to focus, we have received the same data sequence which has been encoded by the encoder. So the data sequence that we have received at the input of the receiver is 0 comma A, 0 comma B, 2 comma C, 3 comma A, 2 comma A, 4 comma A, and 6 comma B. The same sequence, we assume that it has been transmitted by the transmitter, and without any error we have received the same sequence at the input of the receiver, which we would like to decode it. So once again, for decoding purpose, we required a decoding table that is called as the dictionary table at the receiver end. So what dictionary table consists of? Dictionary table consists of all the strings that you have generated at the transmitter end, at the encoder end, and their indices present over here. So this index and string is already stored as a dictionary in the memory of your decoder, and we are going to refer the same dictionary for decoding this particular code. Now if I look at the first string, that is 0 comma A. So 0 comma A is going to be my first string, and for this first string I understand that A is my innovative bit which to be come directly to the output. A is my innovative bit which should directly come to the output, and there is a 0 prior to A. As there is a 0 prior to A, I understand it's a null character, does not contain any index value. Therefore, A will be decoded as it is A. Similar thing happens for B. B also has 0, that is null character. Therefore, B will be decoded as it is B. Then I'll focus on 2 comma C. So 2 comma C. C is my innovative bit which is copied down over here as C. Now before C there is a 2. So I need to refer in the dictionary what is the string for index 2. So index 2, the string is B. So this B is been attached prior to C in order to recover my value BC. Here you are looking the output and string exactly same. Why? Because we have focused a very small string for understanding of this particular operation. So in the larger stream, these string locations will be very less, but the output will go on changing as per the indices present over here. Similarly, for fourth, A is my innovative bit, which is copied down here as A, and for A, 3 is the index. For 3 index, BC is the value which is copied down here as BCA, and I'm going to get my output as BCA. Same pattern gets applied similarly for all the codes. For the last, B is my innovative bit. B is been copied down here. 6 is the string associated with the B. So 6 is the index of string BCAA. So this BCAA will be straightway copied down here as BCAAB is going to be my output, and I can, if I take all these output strings together, I can regenerate my original message ABB, CB, CA, BA, BCAA, BCAAB, which I have transmitted from the transmitter end. Being the data stream is very small, you can easily understand that the string and the outputs are exactly same, and the recovery is a very simple process. But if you apply it to the real-time data, you may get only 10 or 20 strings, but your output combinations could be quite large, and everywhere you have to refer these indices present in the dictionary for decompression of LZ78 algorithm. So I hope you have clearly understood the decompression process as well as the compression process, which I have tried to explain for this example. For more examples, you may try to explore more strings with a larger length, try to apply LZ78 algorithm and try to decode it by using the same decoding table in the similar way what I have shown over here. I hope the things are cleared to all of you. Okay, so we have seen two fundamental Lempel-Ziv codes. One is LZ77 and another is LZ78, and we also try to understand how we can create a fixed length source encoding technique by using Lempel-Ziv code, which does not require any prior knowledge of probability, and that is going to give you some advantages over Shannon, Fano and Huffman, that is variable length codes. So this most popular LZ78 algorithm is been modified by Terry Welch in 1984, and that's the new name has been given to this particular algorithm, that is Lempel-Ziv-Welch algorithm. So that is what the LZW algorithm that we would like to understand over here. This is based upon, once again, dictionary coding technique which has developed by Lempel and Ziv in LZ77 and LZ78 algorithm. Here, what we are doing, we want to assign a fixed length code word to a variable length sequence of the source symbol that we used to do in both LZ77 as well as LZ78 versions of Lempel-Ziv code. This does not require a prior knowledge of the probability, and that's why it is the most popular compression algorithm we are using. The nth extension of a source can be coded with fewer average bits per symbol than the original source, and that's why we could say that much extension of compression has been achieved. Now, where we observe this particular Lempel-Ziv-Welch code, this is very popular code used in TIFF compression like tagged image file format, GIF graphic interchange format, and creating a portable document format, that is PDF. We used to convert a Word file into PDF. We used to compress the PDF document. There is an option in the PDF document to compress that. So for that compression, the general code used is Lempel-Ziv-Welch code. So this is very famous code, a very popular code used in all these formats .tiff, .gif and .pdf file. So we are going to learn this particular popular code, Lempel-Ziv-Welch encoding algorithm. Now, how we are going to implement it, it has been explained theoretically in this particular slide, but instead of going for this theoretical understanding, let us directly focus on the implementation part by taking a simple example for encoding the sequence using Lempel-Ziv-Welch method. So one small sequence has been given here which we would like to encode by using Lempel-Ziv-Welch. The sequence is A, B, C, D, E, F, G, A, B, C, R, D, E, F, A, B, C. Now, to implement this particular thing, the very first step that we have to look at to this particular sequence, and we have to identify the source alphabet of this sequence. Now, what are the source alphabet of the sequence? We understand by looking at to the string that there is A, B, C, D, E, F are present. Apart from that, there is a G alphabet, and apart from that, there is a R alphabet. So my source alphabet for this particular given sequence, it becomes A, B, C, D, E, F, G, R. So this particular source alphabet is only for this limited sequence. If I take a practical case of my text data transmission, I understood that the real-time sequence is nothing but the source alphabet of my keyboard. My keyboard consists of the keys from capital A to capital Z, capital small a to small z, alphabets, numbers 0 to 9, special characters. So all these are nothing but my source alphabets of my source, right? So in real time, these are going to be my source alphabets. For this string, I observe that there are only 8 source alphabets which are A, B, C, D, E, F, G, R. Now, my second step is to store this particular source alphabet into the dictionary of the encoder. So, I'm going to create a dictionary of the encoder where I'm going to store all these source alphabets A, B, C, D, E, F, G, R. By mistake, here E is capital, but basically it is small letter. You can just do this correction here, that all these small letters, they are the source alphabets. They are stored in the dictionary of the encoder, and to this dictionary I have given the index like 1, 2, 3, 4, 5, 6, 7, 8, because there are 8 source alphabets in my dictionary. I hope the step 1 is very clear to you, because here once again I'll repeat the thing. I have to look at to the sequence given to me. I have to identify the source alphabet of the sequence. There are 8 source alphabet of the sequence, and these 8 source alphabets I have to store as a dictionary in the encoder at the encoder end. So dictionary entry is A, B, C, D, E, F, G, R, and its index is from 1 to 8. So that is what my step number 2. Now, in step number 3,
Sir,
yes.
source alphabet means which are not non-repeated.
Yes, source alphabets are the bits, the alphabets which are coming only once, which are not repeating, or you may get the repetitions of the same alphabet in this particular sequence. You will find out that there is no any other alphabet present other than this source alphabet in this particular sequence. That is what your source alphabet. You have constructed this message by using these source alphabets. As I mentioned, for the keyboard, the source alphabets are all the keys which are present on your keyboard. I think, is it clear?
Yes, sir. It's
Okay. Now, next, you have to take the first letter from the sequence. Now I'm focusing on my sequence. What is my sequence? Sequence is A, B, C, D, E, F, G, A, B, C, R, D, E, F, A, B, C. I have to take the first letter of the sequence A, which is at the location 1, and I have to combine this with the next letter B and add AB to the dictionary and transmit 1, right? So what I'm going to do now, I will be focusing on this particular sequence. A is already present in my dictionary. Look at the approach of LZ77 and LZ78. Same way I'm going to follow. I need to create comma separated subsequences in the dictionary, and that subsequence will get appended in my dictionary. My dictionary already contains 8 characters from A, B, C, D, E, F, G, R, which are my source alphabets. Now, to these 8 characters, now I need to go on appending my dictionary by creating comma separated subsequences by following the method of LZ77 and LZ78. So A is already in my system. Now AB is a new phrase or new subsequence with B as the innovative code. So AB I'm going to store in the library as AB, and I will give the next index 9 in my dictionary. So because 1 to 8 is my source alphabet, they're already been covered, and the ninth source alphabet is been nothing but AB. Now, once I have taken AB, a little change in the LZWH is what? I have to start from the later where I have ended, which was my innovative bit earlier. This was not the case for LZ77 and LZ78. So if I just take the, see, you can consider A was my first sequence, which is already in my dictionary. Now second I have created AB, right? So AB I have stored in the ninth location. Now in earlier 77 and 78 we used to start from C, but in LZ Welch I have to start from the last bit of my previous dictionary. It was B, and now I have to take BC together. BC is my unique sequence, so BC will be stored at index number 10. Once again I have to start from my previous last bit CD. CD is my new sequence. I will be storing it in the dictionary at location number 11. Then I will focus on DE. DE is also my new sequence which I have stored at location number 12. EF is also my new sequence. FG is also my new sequence which I am going to store at index 13 and 14 respectively. Then GA is also going to be my new sequence which will be stored at dictionary 15. Now, if I focus on A is already present in my dictionary. AB is also present in my dictionary. So now I have to extend this particular sequence for ABC. So ABC is going to be my new subsequence which will be stored at location number 16. Then once again I will reach to the last part, that is C, and in C I have to take one more sequence, that is CR. CR is my new sequence which got stored at 17 location. Same thing I will go on continuing till the end of the string. I will get the subsequences like RD, DE. DE is already present earlier, so I will take DEF, then FA and ABC. ABC is the last sequence. ABC is already present at my 16th location, so I'm not going to store ABC over there. So I hope I try to clear out first two columns of this particular code, how I'm going to generate the comma separated subsequences in the LZW algorithm. The only difference between LZ78 and LZW is here I have to start from the last innovative bit to a new innovative bit, and in LZ78 we are not considering the last, we are immediately taking the next letter for the analysis. Now, how to create the output? Look at the output is very simple. If I look at the sequence AB, subsequence AB, B is my innovative bit and A is my prefix. For A, if I look at in the dictionary, A is located at index 1. A is located at index 1. Therefore, in the output, I observe that for A is my prefix, A is located at index 1, so my output is 1. B is my prefix for the second subsequence, B is located at 2, so my output is 2. Like that, C, D, E, F, they are located at 3, 4, 5, 6, even G for 7, so my output is 7. Now, I will focus here on ABC. C is my innovative bit and this is my prefix AB. Now for AB, if I just look at AB is present here in the dictionary and the index for the AB is 9. So I will simply transmit 9 in the output. So look at the compression in LZW is little bit more as compared to LZ78, because LZ78 we are transmitting index along with the innovative bit. Here there is no need to transmit the innovative bit. I have to only transmit the index of that particular prefix. Similarly, if I take the case of DEF, F is my innovative bit and DE is my prefix, right? And this prefix is present over here and this prefix is at location number 12. So I will only transmit 12 in the output. So my final output for this given sequence is going to be 1, 2, 3, 4, 5, 6, 7, 9, 3, 8, 12, 6 and 16. So this is what the output of my LZW code. So I hope I try to explain the thing in the better manner. So encoded output will be 1, 2, 3, 4, 5, 6, 7, 9, 3, 8, 12, 6 and 16. Okay, so this is what the encoding of LZW, that is Lempel-Ziv-Welch code. In short, to summarize, step number 1, identify the source alphabets. Step number 2, create a dictionary at the encoder with the index starting from 1 to all the source alphabets. So 1 to 8, 8 source alphabets, 8 dictionary. Append your dictionary by clubbing the sequence of the string that which is given to you. So AB is my 9th entry, BC is my 10th entry. Only the difference, whenever you create these subsequences, you have to take the previous bit into consideration, AB, BC, CD, like that. And what is the output? Output is simply the index of the prefix of the entry made in the dictionary. So the prefix of AB, for the entry ABC, prefix is AB, and for AB the index is 9. So in the output I'm going to say 9 as the output. So the process becomes little bit simple. More amount of compression is possible in LZW as compared to LZ77 and LZ78. I hope you understood the encoding part. Before going to the decoding, let me understand if you have any doubts in this particular process. Okay, now we'll understand. We have the earlier string which was encoded at the encoder side, which is A B C D E F G, A B C R D E F A B C. We have encoded by using Lempel-Ziv-Welch code, and the encoded output is 1, 2, 3, 4, 5, 6, 7, 9, 3, 8, 12, 6, 16. Let us try to understand the decoding part of Lempel-Ziv-Welch. So in the decoding part, we required once again the dictionary, and the dictionary which is used at the encoder, same dictionary is available at the decoder in the memory of the decoder, which starts from the fundamental source alphabets A, B, C, D, E, F, G, R and its index 1, 2, 3, 4, 5, 6, 7, 8. Okay, now I want to decode the given sequence, right? So the input to my decoder is 1, which was the output of my encoder. So 1, 2, 3, 4, 5, 6, 7, 9, 3, 8, 12, 6, 16 is nothing but the input digits that I have received at the input of my encoder. I want to decode it, right? So I have to look at the input to the dictionary. In the dictionary, 1 is nothing but A, so I will reproduce A. 2 is B, 3 is C, 4, 5, 6, 7. Up till this point, I have recovered everything. A, B, C, D, E, F, G. Then I got 9. 9. In the dictionary, 9 is AB. So I am going to take AB in the output. 3. In the dictionary, 3 is C. So I am going to take C over here. 8. 8 is R in my dictionary. So I will take R in the output. 12. I have received 12 in the dictionary. 12 is DE. So my output is going to be DE. 6. Output is F. So F will be stored here. And 16. In the dictionary, 16 is ABC, which will be recalled from the dictionary and stored in the output. So with that, I could get the decoded output as A B C D E F G A B C R D E F A B C, which is my decoded sequence exactly matching with my encoded sequence. So in all types of this decoding technique, the dictionary which you have created at the encoder, same dictionary you required at the decoder in the memory of the decoder. So one by one, whatever the input that you are going to receive at the decoder end, that you will compare with the dictionary, and you will go on reproducing the dictionary entries as per the indices that you have received, and you could able to reconstruct the decoded sequence. So this is what the Lempel-Ziv-Welch code, the encoding part and the decoding part, we try to understand by going through one simple example of certain uh, string of the sequence. You may also apply this Lempel-Ziv-Welch to certain another sequence. A sample sequence is given here. You try to apply it. Now you will find out, suppose this encoded string is BABAA BRRRA. My source alphabet contains only three letters, A, B and R. So A, B, R I will store in my dictionary, and then with the indices 1, 2, 3, then I will create a comma separate phrases like B is already present, so BA, AB, BAA, then BR, then RR, then RRA, like that way. So I could get this particular sequence stored into the memory, and I can create the encoded output. This is another example which you can look at for Lempel-Ziv-Welch. So to conclude this Lempel-Ziv-Welch, what important features that we observed for the Lempel-Ziv-Welch? First feature, the dictionary is created while the data are being encoded. So encoding can be done on the fly. Whereas if you look at the Shannon, Fano and Huffman case, the encoding was not on the fly. You require the prior knowledge of probability. You need to store this particular whole data in a buffer, and you have to go on counting how many letters, how many characters are observed, and accordingly we try to calculate their probability. But here for Lempel-Ziv-Welch, no prior probability knowledge is required, so you can do the dictionary creation on the fly. If the dictionary overflows, then we have to reinitialize the dictionary and add a bit to each one of the code word. So sometimes it happens that the dictionary may get overflow because if your data is quite large, but you can reinitialize the process from any instant. The process will be very simple. Choosing a large dictionary size avoids the overflow but spoils the compression. So you have to make a balance between how much amount of compression you want, or you want to avoid the overflow of the dictionary. But a well amount of compression you can do by using Lempel-Ziv-Welch. Now, here one real life example that I would like to demonstrate for Lempel-Ziv-Welch before concluding this session. The real life example is that I am going to apply this Lempel-Ziv-Welch coding technique for compression of a real-time image. Now, what is real-time image? I have considered a 4x4 part of an 8-bit image. Image consists of pixels, and pixels have certain values, and we understand image looking at the pixel value. If the pixel value is 39 for this two row, it means the color of the image for these two columns is exactly same, whereas there is a drastic difference between the pixel value in the next two columns, 126 rather than 39. But here also we observed there two columns have same pixel value, so similar kind of representation in the image. If I want to apply Lempel-Ziv-Welch for this 4x4 matrix in an 8-bit image, how we can do? So I understand that for this picture I have 8-bit image. So 8-bit image means there are 0 to 255 pixel value. We assume 512 word dictionary format. So 0 to 255 values are going to be my source alphabet. So source alphabet are from 0 to 511 because 512 words are present in my dictionary. All they will stored in the dictionary location 0, 1 till 511. Then I have to look at to the matrix which is given to me, 39, 39, 126, 126. Go on creating the sequence, recognized sequence, right, horizontally. So 39 is already present, 39, okay, is already present. Then I'll take dictionary entry 39, 39. So that is been stored here. Then 39, 126, that is been stored here. 126, 126 stored here. 126, 39 stored here. 39, 39 is already present. So 39, 39, 126 is stored here. Similarly, 126, 126 is already there. So 126, 126, 39 is stored here. Then 39, 39 already present, 39, 39, 126 already present. So 39, 39, 126, 126 is going to be stored as a new entry in the list. Same thing will get repeat for all dictionary entries. Now, these are stored after 255 location. So because 0 to 255, I have already covered. This is my source alphabet. Now I have to start from 256 till 264. Now what is my encoded output? Encoded output is my prefix bit. Prefix bit is 39. So encoded output is 39. 126 is stored at 126. 39, 39 is my prefix which is stored at 256. So my output is 256. 126, 126 stored is at 258. So my output is 258. 39, 39, 126 is my prefix for this entry which is stored at 260. So my output is 260. So on, exactly similar way what we have understood in earlier example. Only the difference, this is now applied to the real-time image compression of an 8-bit image by taking a 4 by 4 random matrix of that 8-bit image. So this way I can go on creating the encoded output sequence very similar to the way which we have explained in the simple example. So I hope I could able to explain you the concept of Lempel-Ziv-Welch by taking a simple example and by applying it to the application of image compression for an 8-bit image with a 4 by 4 sample matrix. The similar way it will get applicable to all the remaining matrices of that 8-bit image, and in the end I'm going to get a compressed code encoded output in terms of the dictionary location as a code word, and which I can transmit and recover back at the receiver plane. In your digital camera, whenever you capture an image, right, this image will first get compressed and then it will get stored into the memory. So for that image compression, the algorithm used is Lempel-Ziv-Welch, which can able to compress your captured image, will store into the memory, and once again it will recall back whenever you apply the decoding algorithm of Lempel-Ziv-Welch. So this is what another source encoding technique, Lempel-Ziv-Welch. So to conclude, we have covered 3 different versions of Lempel-Ziv code. We have started with the basic Lempel-Ziv code, that is LZ77. It is called as basic Lempel-Ziv code, LZ code, LZ77 code. We understood how we have to do the parsing of the LZ code. Then slowly we shifted from binary data towards the sequence of alphabets by using LZ78 algorithm that we have covered in today's session. After LZ78, a little modification which is carried out by the Welch in the LZ78, and we have understood the another compression algorithm, that is Lempel-Ziv-Welch compression algorithm. So that's all for the different types of compression algorithm which are used for real data. All these algorithms are presently used in all the applications, and you can experience them while designing the codes for the image compression techniques such as .zip file, .zoo file, .tiff format, .gif format, or even PDF compression. You will find out all these particular compression algorithms.